What is your question, please?
So when the ship is unloaded,
On the
uh,
unloaded.
yeah. So why do we need to fill the ship with water? Can't we just have an empty ship?
Oh, so the question is that when the cargo is unloaded, so that cargo tank is empty, why do we need to fill up the ballast tank? Is it your question, correct?
Yes.
Okay. The empty ship without cargo is very light. So it's good to operate because you can think about a cargo truck. When it is empty, the truck is very light, so it is easy to run. Speed is run high comparing to when the truck is very full of load. But in the sea, empty ship is very shallow, has a shallow draft. Draft means submerged depths. Say when the ship is full of cargo, the draft is about say 70% of the depth, right? Up to freeboard. But if the ship is empty of cargo and all the tanks are empty, the draft can be very low, say 10%. Then what happens? The motion of the ship is very dangerous because of the wave is coming, wind is coming, and above the water shape is higher and bigger, so wind is blowing more in fact. And another important thing is the propeller submergence. At the back of the ship, there is a propeller, right? But if the draft, this ship looks like a very empty ship. It looks to me that because the red colored one, the ship shows two skin color, gray and how can I say red or orange, not orange. What is the color? Let me say this is red. And draft line is usually saying the between these two color. So if the cargo is full, the ship is submerged up to this color line, two color line. But this ship looks like empty ship. But still they have a submergence about say 20, 30%. I'm not sure, but let me guess. The problem behind the ship, there's a large propeller, which is designed for propelling the ship when the ship is fully loaded. That is a design condition, we say. So for the submergence of propeller, you need to have a certain depth or draft of the after part of the ship. Then you may need to have a, we can say trim. Trim is front part is less draft and after part is more depth, more draft, deep submerge to make a propeller submergence. And that kind of reason, you need to have some kind of ballast water to make a little bit safer submergence to operate the ship. Especially in storm area, high rough sea, you need to have a more ballast water. So captain can control comparing the weather outside and also operational efficiency and speed. Okay? Any other questions? Any other questions? Okay, let's go on to next slide. Standard, and this one is just container ships. And biggest one is
Professor?
right. Go ahead.
I have a question.
Yeah.
Maybe I don't know if it's answered before, but I usually see the color of the ship just below some point. I think usually the draft line
Right.
colored red. Is it coincidence or is there any color coding or something?
Uh, Probably. So for this ship, at this slide set, this ship shows that it is almost fully loaded draft line. So the red colored one at the bottom, but there is another color, right? You see that? Gray colors, white gray, below the red line, right? So this ship has at least 3 colors, right? Previously, it looks like 2 colors. This is typical colors. And those reddish color, this one, it is good for, how can I say, primer or for protection of the steel plate from the sea weather. So there is a salt, more rust is coming.
Okay.
So that this color looks like good for that kind of rust protection.
Okay.
Now, this is a container ship. Container ship has a various loading condition, different loading condition, because it visits many ports, say 10 ports around the trip. So each port has their different loading and unloading. Comparing to the old carrier, when this is a single trip, and it is very simple. Loading full, unloading full. Only 2 options, right? But container ship has very different options, loading cases. So draft line is changing. About your question, the color code, I don't know. But at least they need to show clearly the draft line. That is a regulation. But I don't know whether the color is set to be some color. I don't see, because there are different coloring to each ship, especially above the water. The color is very different for each ship. For underwater, usually their paint is something like this reddish color. And in right-hand side, you see also, right, the reddish colors. There is a draft line shows. And this one in the top is the biggest, not container ship. What is this? Looks like oil tanker. Oh, there is a oil tanker. But length, you see that 458 meters. Second one is a Maersk Line container ship. Third one is a passenger ship, bulk carrier, aircraft carrier. So by seeing the silhouette of the ship, you can sometimes identify what kind of ship it is. And below there is a container ship designed by Hyundai Heavy Industry. And left-hand side, you see that the engine room or superstructure for cabins and pilot house location is different, and the ship length is different. Right-hand side also too. Okay, so different changes, different shapes of the ship containers. And there are also performance requirements for a ship. And basic or principal performance requirement is payload. Payload is how many cargo you can carry. You can think about your cargo truck. Usually, probably the small popular cargo truck is in Korea is a 1-ton truck. 1 ton means the cargo truck can carry up to 1 ton of cargo. Something like that. Payload. Container ship, how many TEU? Right. And speed of the ship. And endurance, voyage distance. That is the 3 main performance. And ship type, conventional displacement monohull. And SWATS is short name of long name. Planning hull, catamaran, hydrofoil, air cushion vehicle, side effect ship. We'll see the next slide. And propulsion plant, diesel engine, gas turbine engine, nuclear turbine, nuclear power plant, electric ship, CODOG, combined diesel or gas, the short name of, and propulsion, the propeller, screw propeller or water jet. There are so many choices you need to as a designer. Right. So this is buoyancy of the vessel. How many slides should I cover more? Oh, many. Anyway, up to after that we can have a break. Okay. So buoyancy is how many weight you can floatable by using the ship, right? Total weight you can carry, including the ship weight together. So I can say that displacement is same as buoyancy of the total buoyancy of the ship. And the power, the weight of buoyancy is coming from different theories. So they classify from right-hand side. That is the simplest one. Is this deep displacement. That is a big cargo ships. Typical. So most popular ships are in right-hand side. And catamaran means twin hull ships. The ship is divided into two bodies, not single bodies like ordinary ships in right-hand side. But there is also variation on catamarans, two different catamaran shapes. But anyway, twin hull hull is divided into two parts. And also there is a submarine. So these are displacement hull, saying that the buoyancy is coming from Archimedes theory. So we can say hydrostatic support or displacement or buoyancy. The same word, one different way. So the hull, the ship displace water, and then in response of displaced water, they put pressure on the skin of the ship. Altogether of the pressure integration, you can get the whole weight of force of buoyancy back. And then conventional displacement hull. This is a small ships. Right-hand side is big ships. But theoretically, those are the same. Conventional displacement and deep displacement. Theoretically the same. Hydrodynamic support, not static, dynamic. And you say this Archimedes theory, here is a Bernoulli theory. Right? So planning hull, submerged foil. Foil is only the ski. This you can say ski, water ski on the bottom of the ship. Surface piercing ski. This is a fully submerged ski, but this is a half submerged ski. Right? Have you have a chance to have a water ski sport? But this Bernoulli theory and hydrodynamic support is the same as the theory we can apply to airplane. But the airplane case, they do not use hydrodynamic support. Instead, there is an aerodynamic support. The buoyancy coming from aerodynamic support coming from using a Bernoulli theory. Right? Pressure difference. You can remember how to solve that lift coming from airplane wings. And then aircraft is in left and right-hand side shape. Here is the aerostatic support, not aerodynamic, aerostatic. So it comes with the air cushion surface vehicle. So they use air cushion, but it's near the surface of the water. That is different. Speed range, 100 knot, 50 knot, 30 knot, 20 knot, 10 knot. So you see this. All right. Let's have a 9 minutes break up to 150, please. Any question before that? No? So see you on 150. Probably, Bereket, you may not have your lecture today. Also, we have a, oh, there is no discussion today. Oh, here is Kim Gi-hyun. I guess you are prepared for discussion, right? But not today, probably next time, on Thursday, okay? So all delayed up to the schedule. All right, see you 150. Vision is there. And we said this is a feasibility study so that the error bound means estimation of the speed, estimation of the cost, estimation of the power requirement is wrong. But how much wrong? The error bound is big in early first design, right? In terms of cost and weight. In concept design, less error bound than feasibility study. So it's layers. Whole envelope, the skin, and internal subdivision, rooms, principal dimensions, length, radius, depth, and whole form coefficient, log coefficient, prismatic coefficient, mid-section coefficient. We'll see next time. Freeboard, deck house volume, hull form. So that old hull form can be modified by computer software. There are famous software called Abema Marine, Intergraph Smart Marine. That kind of software is used for designing of hull skin shape. And this is a procedure, concept design procedure of a Navy ship. So feasibility study, define hull form and deck house configuration, locate deck and bulkhead, general arrangement and configuration development, system design, total ship analysis, and then baseline. These are design 1, design 2, design 3. So you can select afterward by comparing those performances and cost. And 6 critical areas of design integration, the balance between weight and buoyancy should be same. But sometimes the calculation, there can be differences. Then you need to adjust parameters or design dimensions. Stability is important because you see that several accident, probably that is coming from stability problems. Hull girder strength, there's a structural strength. The ship can be broken into 2 parts at the stern. And volume that is required to carry cargoes, containers, energy balance, electric power, steam turbine, compressed air, cooling water. How many fresh water should be used by passengers or shower or drinking, and control, dynamic control, and there is Archimedes. So this water box is full of water, and my weight is 55 kilogram. And if I submerge, then the water is overflow, but they have a device to collect how much water is overflowing, and that is about 5 centimeter, because the side of the box is 1 meter and 1 meter, same box. So that it means 55 kilogram, but my body weight is only 50 kilogram, and the measuring device and line can be 5 kilogram. So submerged weight is only 50 kilogram. So exactly the overflowed water is same as the weight of my body. So that is the way the Archimedes found that the submerged crown is pure gold or not by measuring this overflow weight. I have a similar device to show you as a test laboratory. So next time, I hope TA can find that device and show us the similar experimental show up. So, and then this is same as the body of previous slides, that the total weight of the ship, including cargo or not, should be same as the weight of the ship and weight of the displaced water. And that is same as buoyancy force. So there is a static balance. But if there is a wave is coming and wind is blowing and propeller is running, it starts to become a dynamic balance. But now there is no wind, no wave, no propeller running. So we can say a static balance of total weight and displacement water weight. And there is some video clips, shipbuilding process, hull form design and frigate design for Canada frigate of Navy of Canada. I'll skip over this. So that's it. So I guess, Brakke, you can start your class now.
Oh, okay. Thank you.
Because we have already about 20 minutes left.
Yeah, okay. I'll share the slide then.
Right. Good. Next Thursday, we can start with the discussion session first. Okay? By Kim Gi-yeok.